Hello, everyone. In recent discussions, I've been talking with some friends about torque and leverage and movement about axes, and so these different biomechanical ideas, and they're really fundamental to understanding how the human body works or doesn't work in certain scenarios. Now, for people that have studied biomechanics, the basics of torque might really be small potatoes, but I think this is extremely important. If you work in fitness and you want to have any understanding at all, even a conceptual understanding of what might be happening when you're applying force to a limb or when you're lifting a weight, etc., you really got to understand at least a little bit about torque. So, for example, I have my sloppy handwriting right there. Torque is again can be thought of sort of as a as a rotational force. So if I have a lever here, well, let's see, I have an axis, right, or a pivot point, and then I have some kind of a lever coming out this way, right? And if I apply a force to this thing down on this lever, it's going to tend to rotate. If this thing is fixed here, and so it's a pivot point for rotation, it's going to tend to rotate this system this way. So if I can draw an arrow here, it would rotate it clockwise. Hopefully that makes some sense. Now, how do we measure this though? Well, torque can be expressed as, if this is the force F, right here, so torque would be equal to the force times what's called the moment arm. You can see it written in different ways, but that's the way I learned it. Force times moment arm. And a moment arm is, in this case, the distance between this axis right here and the point of application of the force. Now, it's important, though, that there are assumptions that we're making. So we're assuming that this force is perpendicular to this lever when we use this calculation. If the force is not perpendicular, well, that presents a little bit of a problem. Nothing we can't get over, but it is a little bit of an issue. For example, and let's make this a real world kind of thing. Let's say this is your shoulder joint, and then this is where your hand is, and you're holding something, a weight in your hand, and it's pushing down on you this way. So you want to know how much influence that weight has on rotating your shoulder and making your whole arm drop down. Let's assume that the weight of the arm is negligible just to keep this simple, right? Well, now, depending on where you are, how high you've lifted that weight, that can affect how much that weight will tend to rotate your shoulder joint. Let me give you a little picture here. So let's say we have our axis again, maybe here. And now let's try, maybe we have something like this. We're coming down at a pretty steep angle, right? Maybe like that. The force is still pressing down this way, right? And now, though, it's at a very steep angle. Maybe this is 30 degrees, right? And I know I haven't done it perfectly. It's not actually 30 degrees. But let's assume for the sake of argument that it is. This is 30 degrees, right? Well, now, how much is this weight going to push and tend to rotate this system, right? How much torque is it going to put around this axis? Well, let's say that the force is 10 pounds in both situations. 10 pounds. And it's 10 pounds up here. 10 pounds. Now, if this is, let's say, 2 feet long, right? 2 feet long. What we can do is then just multiply these together, because you remember torque is force times the moment arm. So it would be this 10 pounds times this 2 feet, right? So it would be 10 times 2 equals 20 foot-pounds, right? Now, you can also express it in inch pounds. So this could be, instead of 2 feet, it would be 24 inches. So then it would be 240 inch pounds. That's fine too. The whole point is realizing that there's a direct linear relationship between this distance and the torque and between this force and the torque, all things being equal. Now, let's come back to this situation. Well, intuitively, we might be able to get that because this force is not perpendicular, so it's not coming this way, pushing into the lever, it's pushing at a pretty steep angle, some of that force is not going to go into rotation. It's going to go into translation. So we can actually take this force vector and break it down into two different components. So we've got one component that wants to do this. We could think of like this. And one component that wants to do this. So this would be the translation or translatory component right here. This one would be the one going into rotation. Connect that a little bit better. So we see that this force vector going down, so figure gravity is still pulling this weight down the same way it always did, but now because our arm is lower, its orientation relative to the lever has changed. So we get some of that force going into translation, which is just a linear movement, in this case pulling this way along the arm, and some of it is going into rotation, means it's perpendicular to that to that lever rather, and so it can create rotation about the axis. Now let's cut into the chase. How do we figure out how much torque it's actually generating? Well, because we know this angle, we can figure that out actually pretty easily. We can extend this and make this into a triangle. So if I take, in fact, let me recreate this down here. So I've got this force that's 10 pounds, right? So I'll just put 10 right there. So I'm going to try to mirror these two. And then I'm going to do something like this. Well, let me extend it up a little bit more. And I'm going to make this a right triangle, where the hypotenuse of the triangle is that force vector, that full, what I would call the gross force, the whole 10 pounds that's pulling down. And then I'm going to try to make this an accurate triangle, if I can, or decent, something like this. There we go. Hopefully that does the job. So this is a right triangle. Hypotenuse is the 10, that 10 right up there. And then I use this 30 degrees as the angle that force makes with the lever, that acute angle that it makes. So that's 30 right there. So now, I apologize for my crappy handwriting there with the 3, but that's 30 degrees. This is 10 pounds, right? 10 pounds. And so now all we have to do is a little bit of trig. If we know that the sine, right, of an angle is the length of the opposite side divided by the length of the hypotenuse, we can write that right here. Sine equals opposite over hypotenuse, right? So then we know we can find the length of this side, and this is what we want to find. If this is x, this is what we want to find. Why? Because this is this right here. This is that component. So if this is where the orientation of the lever, if this is the force going down, then this would correspond right here. This leg of the triangle would be the translatory force. This bit would be the rotational force. So all I do is figure that out. If sine is opposite over hypotenuse, that means that x, right, since x is the opposite, so let's do that. Let's rewrite it, equals x over hypotenuse. That means that the sine of 30 degrees, sine 30 degrees, is equal to x over 10. X over 10. Rearrange with a little algebra means x is going to be equal to 10 times the sine of 30 degrees. And I use 30 degrees because it's easy. It's easy to memorize that. The sine of 30 degrees is 0.5. So that's equal to 10 times 0.5, which is equal to 5. And we're dealing with pounds here. So x, the rotational component, is 5 pounds. Now that we know that, all we have to do is go back and multiply that force, since that's the perpendicular force, by this length. So we're still applying the force 2 feet away from the axis. So to find the torque, we do force times the moment arm. But remember, this has to be the perpendicular force for this to work. Well, we found the perpendicular force. It's that 5 pounds right there. So all we do, 5 times those 2 feet right there. So you already know the math. I'm sure you've done it in your head already. But torque equals, right, 5, and of course this is pounds, times 2 feet. So that's just 10. Fully written, it would be 10 foot-pounds of torque. So this is how much torque is being generated at this axis. 10 foot-pounds here, 20 foot-pounds here. Right. So your arm's out straight by your side. You have a certain amount of torque that weight is putting about your shoulder. You lower your arm, so your arm's only 30 degrees away from your side. That's another property of geometry. This would also be 30 degrees. So your arm is just 30 degrees abducted or 30 degrees flexed, depending on whether you're looking at this from the side or the front of the body. It doesn't matter. Your arm's out by 30 degrees. Well, now that weight is only applying half of the torque at this joint compared to what it was in this scenario. So hopefully that makes a little sense. Hopefully that wasn't too long and rambly, but I wanted to make sure that I took the time to explain it properly. There are other ways of calculating torque. For example, we could have found instead a different moment arm and use the same force, but I wanted to explain it this way because hopefully you get an idea that, oh, that downward force there can be broken down or decomposed into a translatory component and a rotational component, and it's the rotational component that we are concerned about when we're trying to calculate how much torque we're getting at a joint.